for today. You see it? Yeah. You see it?
Yes.
Okay.
Professor.
Yes.
I have a question.
Yep.
Okay. So, not for the last lesson, but the lesson before, we said in the equation we neglected the body for the gravity term F. So at the end, I don't understand where the FP at the end, when we have, I mean, we have FP, where it comes from. If you can go to the slide.
PF to be body forces?
Yeah, because we said that we neglected the gravity. Body force.
Now, wait a second. Let's start from this expression here.
Yeah, this expression.
Now, wait a second. The first term now, it's related to, how to say, real body forces. Not to, well, okay. For example, in one of the videos, you're looking at this table that I'm knocking, right?
Yes.
Okay. Well, let's imagine that we have to write the elastodynamic equations for this table. One of the possibilities is to include all the body forces that are really acting on it. And one is definitely gravity.
Yes.
Because it's not floating, right?
Yes.
So gravity is acting, and we have the reaction of the floor that is balancing it. Okay? So we can write the equations, including the gravity here, but it's not useful because now it's balanced. So we can start writing the equations just for transients like me knocking on that. And actually, if I have no hammer here, but let's imagine that now I'm pointing. Okay, maybe here, no, here. But now I'm pointing a force. Okay, this is what we're going to study today. But the first term would refer to gravity. Or if you want.
But the last time we said we neglect gravity. That's,
yes, yes, and we're going to do that. Now this is the Earth. You know,
yes.
The real Earth is much better than this one.
Yeah.
Now we have the volume, we have an external surface, and we have body forces. Why? Because it's self-gravitating system. Now we want to study an earthquake. So we have a surface where we have a shear dislocation. Okay, should we include gravity here? Well, if we would study, let's imagine fluid dynamics, the answer would be yes. But we're studying seismic waves. And gravity is acting on the Earth, but it's balanced in the equilibrium. Okay?
Yeah.
So the first term in that equation is referring to gravity. But, you know, I'm lazy. So I start from an equilibrium where body forces are balanced. We are in the, how to say, in the back door, we are putting them away. They are there, but we neglect them in the sense that, okay, the effect of gravity as a restoring force is not important for seismic waves. It's important for gravity waves. So the first term in that equation is going to be zero due to our laziness. We don't want to put in our bag going to the mountain that because it's not useful. So let's leave it at home. Then we are left with these two terms. The first one is, how to say, related to any discontinuity in the stress, in the traction, like an opening. And we neglect it because we want to study a pure shear dislocation that is there. And we are going to write the third term as if it is represented by a new body force that now is no more gravity, but it's representing the shear dislocation. And there it is. That's the story. So the real body force is neglected, but we can write this term as this one with a force that is represented or representing a shear dislocation on a fault. Okay?
Okay, yeah, I see. Because I was confused between the two F.
No.
Yeah.
This is, okay, let's imagine that this table is made by iron. And I put a huge magnet somewhere. Well, that's another body force. It's acting on the bulk of the system, on the volume, if you want. But we don't care. We're not studying magnetic fluid dynamics. My connection is unstable. Okay. So have I answered you?
Yeah. It's okay.
Okay. Well, what we have to do today, actually, is consider a body force. Because when we have the work with representational theorem, well, actually, that work was based on a definition that we used in the reciprocity theorem. We have used as one of the solutions the Green's function that is the solution of a elastodynamic problem when the inhomogeneous term is a delta. And we defined it and we used it, but we have not solved it. So today's lecture is devoted to the solution of a Green's function problem. And this is what we are going to do, hopefully. So we are going to first consider a sort of a scalar problem. Why? Because it's simpler. And it's a problem that has been solved by previous scientists, also in electrodynamics. It's the problem of a source, of a point source, that is considered to be isotropic in the sense of its radiation in space. And the solution is relatively simple. Then we will move to the vector problem. Why? Because in elastodynamics, we need to take care about direction of the force. Of course, if I'm pushing something in one direction, I'm waiting for a different reaction if I stay in the front, or if I stay aside, or if I stay in the back. That's intuitive in some way. And there the algebra becomes more complicated. But again, we will take some jumps to the end in this case. All the algebra has been beautifully made by, for example, Stokes, Lamb, Green, of course. And we will consider one solution that will be very important, and it will give us two terms, and we will call them near field, far field. The near field will be the term that you are going to use and develop also from a different point of view in Alessandra Borghi's course. The far field is what we're going to use in the next step when we're going to develop the theory and practice of focal mechanisms. And we're going to use it in the remaining part of the course. So this is what we're going to do today. And concluding with this, that will be the expression of the displacement in our beautiful Earth when the fault is no more there, and we represent it as a point source. It will be a double couple. So we will use the far source condition and the far field condition. This is what we're going to use to develop focal mechanisms. Okay? So this is the plan of a journey for today. And what we can use as a start is the definition. Well, these are the same slides that we used during the representation theorem when we defined, in general, a Green's function. You can define it. These are the same slides, so I will just recall them. Every time that we have a linear differential operator, if you want to be a little bit more sophisticated, you have to say that it's a self-adjoint operator. And if you have to solve an inhomogeneous problem with an F here, okay, you can take as a basic solution the one that is the solution of the problem when F is a delta. By delta, I mean it's a Dirac's delta or a Kronecker delta in algebra, whatever. So it's an impulse if you are in time. It's a point if you are in space. It's time and space, impulse, point, and point in one direction, because we have to solve the elastodynamic problem. So let's be recall why it is important, because if you know it, you can write all the solutions using a convolution. So do also, during the last lecture, you have been asking about convolution. Actually, convolution is coming out from this, because if you are using time, the time domain, this operator here is convolution. And this is a general property. That's why the Green's function is often named as impulse function when you're dealing with linear system theory, especially in time. Okay? But it's everywhere. It's in elastodynamics, it's in quantum mechanics, but I'm very humble, so we will stay in the elastodynamic domain, and that's enough. What about the first step, trying to solve, to define the problem? Okay, well, the simplest one is, let's imagine that we have an infinite homogeneous space. It could be a beautiful infinite room filled with air, and I'm putting there a balloon or a cloud. If I'm very careful, well, I could imagine to create a radiation that is everywhere in space, the same. What does it mean? That we can define an initial time t equals 0. An initial point may be in the origin, so it's x equals 0. In our elastodynamic problem, it could be a sort of a beautiful and nice theoretical explosion somewhere in an infinite elastic space. And by the way, we can recall this when we consider, for example, the moment tensor, and we can imagine that we have a beautiful diagonal where we have all the terms equal, maybe equal to 1. So 1, 1, 1. So it's like to have 3 dipoles acting with the same strength in all the 3 directions. So it's a special, not useful for us, case of what we discussed during the representation period. Okay, what can we learn from this simple problem? Well, some properties of the solution, and some properties are already in our pocket, maybe by previous studies, or maybe just by intuition. Because, for example, if we take the beautiful homogeneous wave equation, that is this, okay, and we consider now not equal to zero, but you know how to solve this, right? Let's imagine that the term is zero. Do you know the solution? Please don't make me feel alone here. I'm alone. Well, you have many solutions. Okay, let me stop sharing my screen so you can see the blackboard here. With two visions. Recap, wave physics, recap. I'll be starting the first lecture with this. Now, if you put minus here, this is equal to zero. You can find many solutions. You can use D'Alembert. Every polite function that can be derived in space and time at least twice, with this dependence, will be a solution. Thanks, Monsieur D'Alembert. Merci. We can use it. Do you want to take a safer side? Okay, as an F, we can take an harmonic function. Okay. That's the harmonic solution. Can we use it? Is it useful? There should be a problem in the audio here. Can we use it? Yes.
Yes, no?
Yes, but why? Because now we can thank Monsieur Fourier. Merci. Why? Because he demonstrated that properly summing sines and cosines, we can write any polite function. As we know, listening to our music on digital machines, it's a combination of harmonics. But wait a second. This is a plane wave. What about its amplitude? It's constant. It's never decaying. Is it realistic? Maybe.
No, I don't
No.
think. Because in the Earth, there will be attenuation.
Wait, attenuation is one factor, and we're going to discuss it. But there is one more important factor, that is geometrical spreading. Because if you consider spherical waves and not plane waves,
we divide by the square of the radius, the amplitude by
the square
of the radius.
But what?
The amplitude.
No.
Why?
Energy is going with the square of the radius, but amplitude has to decay as 1 over distance.
Ah, okay, yeah.
Remember, what's going to be conserved on spherical wavefronts, that's R, has to be energy. And amplitude squared is energy. So actually, it has to decay as 1/distance. But wait a second. What about cylindrical waves? Because surface waves are not spherical waves, are not plane waves, they are cylindrical waves. So please remember that for Rayleigh and love waves, the decay is the square root of a distance. Come on, guys. Have you attended the wave physics course? Well, not all of you, but you should know this. So please remember that the general solution of a wave equation, when it's homogeneous, is a beautiful spherical wave. Or, if you want, instead of considering a progressive wave, you can use a standing wave. And then you have to separate this. And remember the relation between progressive and standing waves. The physical interpretation is that summing progressive waves, you can get a standing wave. But if you have standing waves, Fourier theorem, you can generate summing these progressive waves. Remember the duality between progressive and standing waves. When you're looking to model solutions to a problem, like that one, separating variables, also if you're studying the hydrogen atom, you're looking for the modes of the system. And if you know the modes of the system, you can use them to build all the solutions in the system. But my friends, this is not today's topic. This should be already with you. Okay, I'm joking, but I hope now you're recalling things. Okay, let me share my screen again now. So actually, we know how to solve this. This is just the same equation, but in 3 dimensions. And if you want to in 3 dimensions, the wave vector is a vector. It's not just going along X, it's going everywhere. So K is a vector and position is a vector. And that's the scalar product. Okay, this should be undergrad physics, but it's a recap. So now, let's consider, and I hope that we can start with this journey, let's consider the first non-homogeneous problem. Now we have a point in space and in time where we make a beautiful, symmetric, peaceful explosion. Okay, actually, there are many ways to solve this problem. I'm going to take a shortcut and go into the solution. Actually, everything is based on a solution of the Laplacian operator that is here. And if you consider when time t is equal to 0, this is going to be in some way 1. Well, the solution can be written like that. Oh, we know that. It's D'Alembert. Thank you. When we consider now time and the solution except when you have a Poisson equation like this one, so t now is 0, and we know how to solve it, And most of the algebra, I'm sure that you have used it to find the electric potential field from a charge. It has exactly the same expression. And now when you consider the time varying, what you have to replace here is a retarded time. So this is very intuitive because you have to wait for the message from the source to arrive at your position R after a time that is position divided velocity. It's called retarded time. Good. Everything is beautifully symmetric. This 4 pi is coming from an integral over the, let's say, the surface, and this is the spherical, how to say, conservation of energy, if you want. It's the integral, 4 pi r. It's fair. This is easy. Unfortunately, it's not the solution of our problem. Why? Because here we're missing a delta in direction. Our problem is not isotropic, but we can use this. And actually, this problem can be used also to expand these properties. How? Like that. For example, if we move the source point in space and time, what we have to care is actually to shift properly space and time. It's not a problem. Also, if our source is not in the origin and it's starting at t equal something, sometimes, we have just to take care about it. Second, let's imagine that now the function in time is not a delta, but it's like your favorite singer singing a melody. So it's an f of t. Well, the linearity of the problem is saying, good, take your singer recording and just time shift it and convolve it by the problem. And I'm not joking, because this is used from an acoustic point of view in many tricks for home theater. So if you want a famous actor to sing in a forest, you don't have to take the actor to the forest, or actress to the forest. You can record the forest, you can record the actor, and then you convolve it. Nice. Now, what if instead of having a point source, let's imagine that we have a source of a volume source. Well, we can break that volume in small pieces, as since the operator that we are considering is linear, what you have to do is to sum all the single contributions. And actually, until now, the problem is not only elastic, it can be used in acoustics, it can be used in electrodynamics. This is the radiation of a charge or whatever that is creating some current felt somewhere, sometime. So up to now, no news. Okay, it's important. You see, everything is simple from a conceptual point of view because the operator is linear. But the new difficulty here, in our case, is due to the fact that, some parts were supposed to appear, sorry. Okay. I changed the slide, so, okay. Now, this was supposed to appear before. This is a recap. And it's impressive, I know. Okay, let me fix it. Sorry, because it's a new one. Animate, appear, by object number 4. This has to be number 2. Otherwise, I will never remember. This has to be appear. This has to appear. What is it? Oh my God. Sorry. That has to appear. And this has to appear. Let me group it. Who knows if now it's working? Okay. Now, what is our problem? Let me stop sharing and using better the blackboard. Okay. So, to recap, if we have inhomogeneous problem solved, inhomogeneous solved. So this is done. This is done. Now we have an additional complication here. Our delta is not a beautiful isotropic force. It has a direction. So it's a delta also in direction. We have an additional delta here. So are we going to push in that way, or to pull in that way, or in this way, or in this way? This is adding a geometrical complexity. Do you understand this? So the question is, can we go on?
Yes.
Okay. So how to deal with vectors? Well, for example, in my wave physics course, usually I'm solving the wave equation in 3D for the elastic problem using Helmholtz theorem. Helmholtz theorem is a very important piece of, let's say, applied maths that could be very important to solve problems. For example, you can use it to separate P and S wave fields. Because the P wave field that is connected physically with longitudinal waves that are compressions and rarefactions in a solid is related to this part. While shear waves, S waves, that are related to transverse waves that are shearing the medium are related to this term. So usually in wave physics, elastic wave physics, Helmholtz theorem is used to separate the solution of a wave equation. What we are going to do today is to use it to separate the inhomogeneous term that is another vector. So this slide here is just a recap of Helmholtz theorem. What is saying? Well, actually, it's more complicated than this, because from a mathematical point of view, you have to add some conditions about the politeness of the vectors. But in our classical physics approach, these conditions are satisfied. So essentially what it is saying is that if you have a vector field, U, but usually E is the displacement field, but okay, whatever, you can always separate with a unique representation. It's a sort of a representation theorem in terms of the gradient of a scalar potential plus the curl of a vector potential. So you could say, so what? Why we should replace one vector field with two potentials? Well, because the two potentials have different symmetries. One is scalar and is connected with the gradients. It's like P waves. The other one is vector and it's connected with the curl, and curl is shear. Just as a piece of a demonstration, that is a hint for a demonstration, I don't want to make the full story here, is that you have how to find, well, the game is, okay, I give you U, please find me phi and psi. Okay, what you have to do, the animation is not working. What you have to do is to consider the Poisson's equation related to U and solve it. We can knock on mathematician's door, it's full of them here at ICTP, and they tell us, okay, that's it. What you have to do is to make a volume integral, and you take your vector, you take this 4 pi, it was already there, and you compute that. So given U, you can compute W. And then you use another vectorial identity. The Laplacian can always be written as the gradient of a divergence minus the curl of the curve. What the hell is this? Well, it's always used, it has been used also by Maxwell to clean EM equations. By the way, if you use this identity with this, you find immediately that you can find the scalar potential taking the divergence of a W that you can compute, and the vector potential will be minus the curl of W. Okay, as I told you, this theorem can be used, and usually I use it, when you have the elastodynamic homogeneous equation and you separate that equation into two wave equations, P waves, S waves. What we have to do today is to solve that equation with P and S, but now with an additional term. And the game that is at the base of the Green's function of elastodynamics, as solved by Stokes in the 19th century, was to use the same theorem to represent the body force. So in order to be able to separate the problem into easier pieces. Okay, it's time to start. That's the real start for today. Okay, this is the elastodynamic equation that is containing two wave equations with this term here. Wait, now today F is a real body force. It's not gravity, but today is our force. This is what we have to solve. If F is 0, solution will be easy, P and S. You use Helmholtz Theorem and you will divide this equation here into two wave equations, P and S. And here you would get Vp divided by rho square and Vs. Okay, the new friend for today is F. Are we together until now?
Professor, here,
I hear you.
yeah, here, F is our inhomogeneous term, right? It's a delta.
Today is a delta.
Okay.
It's like, do you see the table in one of the screen, in the Stasi lecture hall screen?
Yes.
It's like this. Okay? Or this. Or this. But it's a delta now. Well, I'm not a delta. My finger is not a delta, but you can imagine that it's pointing in one direction, in one point, and I will start at a given time. That's our F for today.
Okay.
Okay? And we did nothing until now, just, okay, collecting, putting the pieces in our bag. Okay, this is what we have to go. This is the map where to go today. Okay, the journey has been made, not by us. It's like to follow an alpine way already explored. And the exploration, the story of the exploration starts here with these messy writings here. Now, okay, the idea is to break that equation in terms of equations that we can solve. Okay? One other statement that I want to add now. I hope it's trivial, but remember, this equation is for isotropic, homogeneous, beautiful, elastic space. So it's the simplest case that we can imagine. And in this space, we know that the solutions should be made by P waves and S waves. There are no other waves in a space like that. Of course, if we had a free surface, wait a second, reflections and Rayleigh waves. If we had a layer, a low velocity layer, we would have Rayleigh and Love waves. If we have more boundaries, we have all the reflections and refractions of body waves. But in this simple case here, the simplest possible case, we are waiting for a P wave and an S wave. What will be the difference is that P waves and S waves should be weighted by a radiation pattern. What I want to say is that if a force is pointing this direction, on this side and this side, we're going to weight something different. So a kick in this direction or a pull.
This prof, my network was unstable. I said my network was unstable. When you started, right? I said my network was unstable. The internet was unstable. So when you started writing on the boards, the network be frozen again.
Sorry, Jacobo, I don't know how to help you.
Can you hear me?
Yes.
I said my network was unstable. So when you started writing, I couldn't hear.
Oh, okay. Okay. What I'm trying to say is that if we have a force pointing in one direction, we are weighting a different pattern if we stay here, if we stay there, or if we stay here or here. So we are waiting for a weighting factor about amplitudes. And this is what we are going to find. So just in short, what we are looking for today this is what we have to find. These are the news. Because in the inhomogeneous problem, okay, we have a P, we have an S, we can treat them as spherical waves, but amplitude is the same everywhere. Of course, it depends on the distance, so amplitude will be shorter, smaller, if we are far from a source, but no other factors affecting amplitude. Today, some news will arrive. Okay. So, Jacobo, is it okay? Good. Now the tough part is starting, but we will jump. Just looking at the main logical steps. So, we have a problem, homogeneous, infinite isotropic space, so it's characterized by it's an elastic space. So we know lambda, mu, and rho. Good. And thus we know Vp and Vs. Okay? Good. Now, what about the body term, initial conditions, boundary conditions? Oh, we have no boundaries here. It's infinite. Okay, all of them can be written using Helmholtz theorem. All of them. Because Helmholtz theorem can be applied to any polite vector field. By polite, one of the most important conditions is that, okay, you can compute derivatives, at infinity it's behaving well, so you don't have some strange blowings at the infinite and something like that. Okay. And so you can write all the pieces of this equation like that. Then, and this is Lamè's theorem, that is an application of the Helmholtz theorem, you can demonstrate the two potentials exist so that you can write U as the gradient of a scalar potential plus the curl of a vector potential. The vector potential has zero divergence, like for S waves, and they have to obey these two equations. So you can say, so what? Well, look at these two equations here. We know them because actually, if this term and this term, had be zero, these equations would be P-wave equation and S-wave equation. Today's problem is concentrated mainly about those two terms. How we are change the solution? Okay. Let's consider one example, just to see what is the logic applied to a specific case. Let's imagine that our f now is a function of t, good, applied somewhere in x, maybe at the origin, and applied along the x direction. Okay? Helmholtz theorem is saying, okay, you can write it, you can re-express it, you can represent it in terms of a gradient of a scalar potential plus the curl of a vector potential. How to find them? Poisson equation. Thanks, mathematicians, because what we have to do now is to write the W associated to the Poisson equation. And there you go. And here it is. Oh, so nice. Now, following Helmholtz theorem, we can find the two potentials that will represent Vf. And you take the divergence and minus the curl. And there you go. Now, these are the two additional pieces that we should add to our wave equations. Please note that here we do have directions, because this partial derivative and these two partial derivatives are representing directions in some way. This is the spatial dependency, this is the integral over spheres, that's fine. But here you're getting directions, well, along 1 essentially, and 2 and 3. Now the problem is to put these two pieces into the wave equations and solve them. Should we do that the part? No. Now we are going to take an elevator. Yep, it's not polite in alpine walks, but okay. Unfortunately, we have not enough time to, and also my capacity, to write all the passages here. But what we should do is to solve these two equations here, putting capital phi and capital psi using those two terms. Should we do that? Well, maybe yes, but we will not do that, and we will use the beautiful piece of work by Stokes. And he was not only solving that specific problem, but he was solving the general problem, where the delta can be applied in any direction. And he was just using the spatial derivatives that are just representing direction cosinus. And now the solution of the Green's function for our elastodynamic problem is this. Oh, we are on the top of a new mountain now. Wait a second. Question number 1, is it nice? Oh, yes. Please take a picture from this top. But you should say, okay, we were waiting for some landscapes. Are these landscapes there? Yes, here in the blue part. Because in the blue part, what we do have is a P wave and an S wave. Because you see that the retarded time is connected with P wave velocity and S wave velocity. So one is arriving first with a compression. The other one is arriving later with shearing. So on this top, we could see, oh, these are the mountains, the other mountains that we were supposed to see. There they are. But we have a different view now, because actually, here, if you put a delta here, you would get a delta here, so no news here. The news are here. What are the news? Well, not in the 1 over x. These are spherical waves. That's fine. But the news are here and here, because these two terms are the radiation patterns. And they are telling us, okay, according to your point of view, you will feel differently P and S waves. And you will see in the next slide how they appear. But wait a second. So the blue square, the blue frame, is containing the view that we were waiting for. P waves, S waves, now weighted by a radiation pattern. But what about the yellow one?
Please, Professor, just small question.
Wait a second, because I'm going to ask you a question. Okay. And then you can. Now, look at the yellow frame. That part, where it comes from? Well, it comes from the solution, of course, but we were not waiting for it. Let's give a look to this term here. Now, it's decaying with the third power of distance. It's not a P wave, it's not an S wave, it's a combination. It's arriving after the P, of course, it has to. And then it's containing both of them. Well, take a message home. And this slide is trying to show the most important message for today. The blue frame is containing what we wanted, because it's containing the proper P wave, this. So please look at not at the details, the main features here. Alpha and beta, Vp and Vs. And you know them. From these ones, given defined the properties of our elastic space, lambda, mu, and rho are given. Vp and Vs are given. We have no inelasticity yet. We have to wait for. We have nothing. We have no boundaries, no discontinuities. Everything is clean. We have Vp and Vs. So alpha and beta are numbers, velocities. X0 is nothing else than a source function. If you want to stick with the proper definition of a Green's function, you can put it as a delta. And you would have a delta here and a delta here. 4 pi and rho were already in the isotropic solution. The new terms are actually this and this with the third power of the velocities. Now, 2 questions, and then we will make a pause here to take pictures on the top of this new mountain. Question number 1, that's easy. Which one is largest? Alpha or beta? Second question, what about the yellow box? Now time for you. So Tarek, if you wanted to ask your question. Oh, first, please, Tarek, first, it's your time to answer to my first question. What
Okay,
about alpha and beta?
You said who is bigger than the other. This
Yep.
was your alpha is representing the P waves, so the P waves will be bigger than the S wave.
They're faster because
Faster, yeah.
lambda plus 2 mu will be always larger than mu.
Yes.
And if you take a fluid, mu is 0. Vp is something and Vs is nothing.
Yes.
Okay, so from your answer, you do understand that S waves on average will be larger than P because alpha is larger than beta.
Yeah.
Okay. So now it's time for your question.
Actually, I forgot my question.
So, okay, maybe.
Professor. Professor.
Yes.
The larger that we are talking about, is it that the S wave is having a higher value of the velocity, like it's having a higher value of velocity?
No. I was saying that S wave velocity is smaller than P wave velocity. And since it is at the denominator, on average, because in the next slides, we're going to find something. On average, S waves will be larger than amplitude, will be larger in amplitude than P waves, because beta is less than alpha, on average. Okay, now wait a second. We will make another pause in 5 minutes. The message to take home today is that, okay, if you put a body force that is a delta in time, a delta in space, and a delta in direction, we get P waves, S waves with their radiation patterns and an additional term that is called near field. You know why it's called near? Because look at the decay. Here we have 3, here we have 1. What does it mean? That sooner or later, the amplitude of the yellow box will be negligible compared to the blue box because it's decaying faster. A tricky question could be, okay, where the near field will vanish and only the far field will be left? Well, that's a tricky question. And to properly answer, we should use the theory of Hankel functions. But I don't want to knock again into the mathematician's door. So let me tell you a simple answer. A simple answer is that the far field will be the dominant one when k, the modulus of a wave number, times the distance is much larger than 1. Do you want to write it in a different version? So when the distance will be much larger than wavelength. And so now let me tell you, well, wait a second, because I want to tell you something important. Please do remember from now on, but when you say near source, far source, and when you say near field, far field, this naming has different meanings. The near source, far source, we defined it in the representation theorem. And it was related to the fact, to the assumption, okay, can we consider the point, the source as a point? Near? No. Far source? Yes. Today, we're using near field, far field, and we are discussing just a point source here. It's a point. Now we're simply saying when the near field can be neglected for a point source. What we're going to use on Friday is the condition of far source and far field. So the source will be a point, and from its radiation, we will take just the blue box. That's the simplest condition that we can imagine. Tarek, before you asking questions, let me move to the next 2 slides, because maybe they contain the answer. And if you forget it, it happens.
No, I remember the old question.
Okay, do you want to ask it now?
Yeah,
Go.
it's just about the radiation path. You said the radiation path. It means
okay,
that
it's coming. It's coming.
Okay, so okay.
It's coming because now it's time to give a look to these 2 terms.
Okay.
Okay, let me show this later. What about the far field? That will be the one that we're going to use from Friday on. But please do remember that the near field could be very important, as I'm going to say to you, I hope, in 2 minutes. Now, what about the far field, the blue box? Well, that was the view that we were waiting for. It decays as 1 over r, spherical waves. It is made of P and S. Yes, waiting for it. The waveform at a given point in space will be characterized by a retarded time we need for the waves to arrive us. Okay, good. But the fourth property contains the news that we were waiting for. It has a radiation pattern. And if you work out the direction cosines in a specific case, you will see this pattern. And this maybe contains the answer to your probable question. Probably contains the answer to, wait a second. Let's imagine to look at the force from the top, okay? So now we have that force there, and we look at the radiation from the top of it. The P waves radiation pattern goes as the cosine, and the cosine is now we're looking at the top. It's going as the cosine. What this plot here is saying is that if we stay in the front of a force, we're going to be pushed. If we stay in the back, we're going to be pulled. And that's reasonable. If we stay on the two sides at 90 degrees, no effect there with P. What about the sine? Well, what about the S waves? Well, it will be complementary. And what we're going to feel is nothing in front, nothing in the back, a maximum shear in one direction, and maximum shear in the other direction on the other side. And so now we can imagine the simplest synthetic seismogram, because in the point source, far field conditioned in a homogeneous, infinite, elastic, isotropic space, this is our seismogram. Okay, we stay at a given distance from the source. We have to wait for the P wave to arrive. It's going to push, to pull, maybe nothing, according to the angle. Then later, the S wave will arrive, and according to the position, could be maximum shear, maximum in the other direction, or nothing. It depends where we are. Okay, this is what we were waiting for. Message to take home. What about the other term? The other term can be rewritten in a more useful fashion and using what is called the Heaviside function. Heaviside is, you know, it's the step function. Well, you can write that integral as this. What do we notice here is that we have a radiation pattern that is multiplying this quantity. Oh, I'm stuck here. Do you hear me?
Yes.
Yes.
Okay, because my cam in the Stasi room is stopped. But okay. Now, okay, now it's okay. The Wi-Fi of ICTP is bouncing. By the way, if you want to plot it, there is one important news here to remember. Okay, you see, rewriting it, it contains two factors that are rapidly decaying compared to the far field, and they are made like that. One is like that, and one is like that. And what is important is that at the end of a story, they are not going back to zero. You have a permanent tilting there. The amplitude of this tilting will depend on the radiation pattern and on the distance, because this will decay faster than this, and both will decay faster than the far field. But if you stay near to the source, you have permanent dislocation there. What does it mean? That if you have a GPS around it, you can record it. And maybe you remember the first lecture when I was showing to you some pictures coming from the Toku event. And if you remember, some of the GPS signals and seismograms were showing a permanent tilt. I think I've left, what's happening here? Okay. I want to, no, not stop sharing, but I want to open the original one. Let's see if I have left, no, but I want to show you the first one. Wait a second. Oh, God. Do you see it? No. Oh, sorry, I'm trying to reconnect. I think
No, we are still, yeah, we are still able to see you and hear you.
Yeah, but not on my cam.
Okay.
Let me try again. It was disconnected by Wi-Fi. Now you should. It's getting slow. I'm sorry for that. You're not looking at my screen.
No.
I know it's stuck. Oh.
Now we
Yeah,
can
it
see.
has come. Now we can see.
Oh my God. Sorry, it's not my fault. I cannot do anything here. Do you see it?
Yeah.
Yes, yes.
Okay. This is one of the slides that we had been looking at during the first lecture. Now look at this. This, a little bit here, nothing here. Okay, this is the static displacement that has been left on the ground by the near field. Actually, if you have a panoramic view of Japan, I was showing to you this picture here. Look at the arrows. Their amplitude is very large, near to the source, and then decaying very rapidly. And so if you have a GPS network, you can record it. That's the near field.
Yeah, agreed. Yeah.
So this is what you're going to discuss in Alessandra's course, and the basic piece of theory that you can use actually is this one, because you have a radiation pattern, you have an amplitude decided by the medium and by the distance of the source. Okay, now before going to the last slides, any question?
Yes, just for summarizing. So the near field is like a local displacement, yes?
Local.
Near the field, I mean, near the source.
Source. But actually, now, properly, the source is a point, because it's a single force, right? So it's local in the sense that it stays near the source. But we shouldn't call it near source, because when you use near source, it means that the source is extended. So it's a matter of terminology. if you want to use proper terminology, if you say near source, then you see the source extended. If you say far source, the source is a point.
Okay.
Now let's consider far source. The source is a point, and you can be in the near field of a far source, or you can be in the far field of a far source, or you can be in the near field of a near source. And so the source is extended. Every single contribution has pieces that contain the near field. And this is what we are going to discuss in the final slides. Very rapidly.
Okay.
Okay, let me try to go through the final slides. Because, okay, we are tired. We have been climbing also this new mountain with a beautiful landscape. Some mountains are beautiful from here, and we have noticed that there is a new one, the near field. But we have to make a final piece of the walk, because the representation theorem was saying us, okay, you can represent the source with a set of equivalent body forces. You can assume that you are in the far source condition, and the source is a point. But for a pure shear dislocation, the point source is not a single force, it's a double couple. So what we have to do now is to take a single force, take an arm in one direction and compute the resultant, take another force, take an arm in another direction and sum these two double couples. And we are tired. Yes, let's take the final elevator. That's the final view, but we are too tired, and so we just take a snapshot. But this is what we're going to use in the next lecture. Because, okay, we spent most of today's lecture in solving pieces of the Green's function. First, the isotropic one. Then we have used Helmholtz theorem and Lamè's theorem to find the solution for a single force. Now we have to use this in combination with the representation theorem and compute the displacement field for a double couple or for a moment tensor. Well, it's just a matter of algebra. Because if you do remember, one of the expressions that we found may be the most useful in the sense that it's the most common to be used was this. Now, what is Mpq? Well, it's the moment tensor, please remember. It's a symmetric tensor. It can be diagonalized. You can find 3 eigenvalues, M1, M2, M3. For a pure shear dislocation, their sum is 0, and one of them is 0. Okay, we know that, and we have a double couple. But in general, we may have 6 independent terms, and maybe we can have also the diagonal. So we can imagine that each component of a moment tensor is a couple of forces, dipoles or couples, if you remember. Okay, maybe I will be 5 minutes late, but I want you to look again to one of the slides of the representation theorem. This, do you see me? Oh, there is a delay, wait. My internet connection is unstable. No, I don't want to show you. Okay,
Yeah.
this one. Okay? Now you see, any term of a moment tensor actually is a single force, an arm, and another force, as we found. Okay. So the final algebraic step would be to solve this problem, where here we have, okay, it's low, sorry. Please resist for 5 minutes Wi-Fi, okay. We have a force in a given direction. We have an arm in the other direction, and we have to convolve it with the time, oh, sorry. But this is referring to the homework. We have to convolve with the spatial derivative in the direction of the arm of a green force. Why? Well, we have a single force in P direction, we have an arm in the Q direction, and we have to take this one. So we know the solution to one force, we have to take an arm and add the solution to the other one. Okay. The solution to that problem is this. And it has two beautiful colors, 3. Why this naming here? Well, let's start from the far field. And this is what we're going to use on the next lecture. Do we recognize it? Yes, it's a P wave. Sorry, it's an S wave. It's a P wave. It has a retarded time. It's a spherical wave. What about the time function? And this is your homework. Your homework could take 1 minute or 1 day and a half. Because there is one thing here. It's not a fly on my slide. That's a dot. And we have a dot here and a dot here. So the time function that is in the moment is there, but with a time derivative. And your homework is to tell me why. It could take 10 seconds. Actually, it could take 1 second. But to me, it took some days at the beginning. Okay. The blue box is containing what we're going to use in the next lectures. And from that one, we're going to work out the focal mechanisms. What about the other 2 boxes? Well, they have different names. Why? Well, because if this is decaying as 1/4 distance, this is containing the 2nd power and the 4th power. So you can put them together and call them near field, but actually it would be more accurate to call them near field and the intermediate field. Both will decay faster than the far field. And if you want to be sophisticated, actually, if you want to use this theory to model the static displacement left by an earthquake near the source, actually in the near field, using GPS and calling them coseismic displacement, you should use these 2. Do you want to see them? Haha. Wait a second. Okay, there it is. On the left, and you're going to discuss this with Alessandra. On the left, you have a displacement left on the ground by the L'Aquila event. Okay, the magnitude was 6.3. And you see these patterns found by INSAR, these are fringe patterns, interference patterns. And what you see there is the static displacement left here. Then it's 0. It's vanishing away from the fault. And this is just a new picture coming from the Toku event. So coseismic displacement, coseismic deformation is in the near and intermediate field. Let me make, and it's this. On the bottom right, I don't want to enter into the details of this. In the bottom right, you have a double couple, and the arrows left around the double couple with its radiation pattern. And the final piece of this excursion for today is the picture on the left. Because this is the reference system that we're going to use in the next lecture. What do we have there? Well, if you remember the specific case that we considered, yes, on Monday, for the representation theorem, we considered a fault. The dip was 0, the slip was along x direction, and we discussed the representation theorem. And in the representation theorem, we found that, okay, we can replace it with a double couple in the far source condition. Today's lecture is telling us more, because according to the relative position of a receiver around the fault, now we have a tool to predict the amplitudes. And the usual reference system is centered on the fault, where we know we have strike, the dip, and the rake. And the strike of the fault was the angle that the fault is forming compared to the north. Good for geology. But from today, we are going to use another angle, because now we can imagine that we are a receiver, and the receiver is around the fault. And now the most important angle, or couple of angles, is the one that is telling our position respect to the source. And for example, we can use this couple of angles telling, okay, how we are in this direction and how we are in this direction. So theta and phi, instead of describing the fault, they describe the position of the receiver respect to the fault. Sometimes this one is called strike receiver. And we can express the radiation pattern in terms of these angles that are actually direction cosines. And if you want to use a formula with Alessandra, maybe she hates this formula, but she's using this, it's like that. So it's predicting the amount of displacement somewhere around the fault according to the distance, according to the position, and what is left here is the moment tensor, but in its amplitude, so the seismic moment. So the amount of slip depends on M0. Please remember this. Now, what about the radiation pattern of the far field? Well, here I spent 1 hour in writing this. And what we're going to use, so this is the radiation pattern for the near field, the intermediate field, okay, useful for Alessandra. And this is what we're going to use. It's simpler. And the blue box that is here, the blue panels that are here, are containing what we're going to use on Friday in terms of radiation pattern and in terms of signature left there. So final slide for today is this. It's a prequel. It's a prequel of what we're going to discuss. Oh, you have to wait. There is a delay. Okay, here it goes. This is coming from Aki and Richards. And this is the idea that we are going to discuss on Friday, going towards focal mechanisms. Because now we have a point, far source. We are in the far field, so far source and far field. We know that we can use a double couple. And now we know what the radiation should be around the double couple. And if you imagine to take phi equals 0, if you look from the side, according to theta, the angle describing the position of the receiver around the fault, so we are looking at from the side, the fault, well, what we are waiting is big plus, big minus, big plus, big minus in terms of P waves. So we have 4 quadrants. If you want to see, it's like that. If you imagine to put a ball, actually it's called focal sphere, around the point source, that is a double couple, looking at it, we should have 4 quadrants with pluses, minus, and 2 lines that are 0. Actually, the focal mechanism is a representation of this ball here. And this is the same idea for S waves, but please remember that S is not taking compressions or rarefactions, plus minus, we are taking shear. So it's a vector information. Actually, it's coming from the vector potential of the Helmholtz theorem. So, my friends, my connection is unstable because probably Wi-Fi here is tired as myself. This was the second tough journey that we took. Representation of theorem, Green's function. And I know that you and myself are tired. That's why on Friday, we will take a sort of a gentle tour using the far source and far field condition to make some nice representations. But we'll end up, let's see if I still have it here. I know it will be, wait a second. They will be giving us, you have to wait, everything is low here. My goodness. This, please wait, delay. It's already on my screen, but not on, not that, not that. This is focal mechanism representation. Now we have all the tools, except one, to understand this page. And this is what we're going to do on Friday. In principle, it will be more relaxing compared to the representation of theorem and Green's function. I know, 2 tough arguments, but they are the only way to understand what is seismic moment, M0, that will become magnitude in 3 lectures, and to understand the basic theory of the coseismic displacement. That's why we have been spending this terrible time together on these topics. Okay, let me salute you, telling just some tiny things. Please, if you have questions, we will discuss them on Friday. Second, remember your 1 second or infinite time homework. It's related to this. Why the dot there? It will have deep consequences. So this is the second part. Third, on Friday, since I have an exam, I have to make an exam to some students in a different room at the university, I will transmit from a different building, but I will be in a place with a beautiful blackboard on the back. And I hope a very good speedy Wi-Fi. So we will visit together a new building that is not the Central University, is not the Stasi room, it's not my room with Star Trek. It will be a room in, for speech therapy students, because I'm teaching acoustics there and they have an exam on Friday, just 10 minutes after the end of this course. Okay, so these are the three tiny things with which we are going to update on Friday. Think about the dot. This is not a fly. So it's not a couple of flies. Could take 1 second. So it's time. So let me say you have a nice, beautiful afternoon, and let's meet on Friday. Usual time, I hope, but different space. Okay?
Okay, bye.
Goodbye. Let me stop
you.
sharing here. Let me close.
Thank you.
Yeah.
Yes, tell me.
Yes, I just was wondering something, information regarding the recorded lessons, if that would be possible to have them. I don't know if someone has information regarding that matter.
Okay, that's a good question. Maybe I will ask later to the guys here that are helping with this stuff. Let me ask you to the diploma students, where do you find, they should appear also on YouTube because, but you know,
I've sent the secretary an email and
Yeah,
okay,
we have
she
some.
have not responded.
Jacobo, or any of you, if you can share the place, the repository for the movies or the YouTube, because you know, on YouTube, I'm just listening to old rock bands, so or some maths, but no lecture. I'm too old for that. So if one of us can share with us the information about the repository, you're very welcome. So Maria Aurora, I think, or Jacobo or Tarek or Dung could help us. I cannot.
Send me your
there
email.
there is past lessons in YouTube.
Okay.
Okay.
So let's send
or,
your email or
That will be fine. Thank you.
yeah, in the chat.
yeah.
Thank you. I have no social media. I was deleting all of them, so but I have YouTube. Okay. Thank you.
Thank you, everyone. Thank you, Professor, as well. Yes.
Okay.
Okay. Yeah.
Good Friday.
See you on Friday, everyone. Okay, that's my email. That will be fine, guys. Yes, if you can kindly help me.
Okay. It's not a problem.
Okay, guys, I'm leaving also from here. Okay.
Okay, bye.
Okay, thank you,
Professor.
Professor.
Thank you. Bye.
Have a nice day. Okay, so
I will send
Let me send you the. Let me go there and send you the links. Let me. Hang on.
So they are all on YouTube.
Yeah.
Yeah, but
you cannot see the professor because he's sharing his slides and you can just hear him.
That's fine. That's more than nice. Yeah.
Yeah. So ESP.
If you can share the link so I can check them. I can check them later.
Yeah, let me copy the link. I'm coming. Oh, I'm coming. Yeah, my email is.
Okay, I sent it to you. I sent you the link. Have you received it?
Just a second.
No, not on email, on the chat.
I've sent to your email too. So check both this chat and the email.
Oh, thank you. Yes, I received an email. Okay.